The last section in the chapter is called Quadratic Systems. Kind of like systems of equations in a previous chapter that we were working on where we had a bunch of linear equations. Now we're going to have a bunch of systems of equations that aren't linear. You might have a line and a parabola. You might have two parabolas. Okay? And the goal of this section is to find where those equations cross, just like it was in the last chapter. So in section 4.7, this is our friend the smiley face again. We put a mouth on this face. Now we want to make a mouth that's open using two parabolas. So we kind of probably want to make something that looks like this. No. So let's come up with just a smile first. I need an equation that gives me a smile. Use vertex form. Y equals x minus 4 squared. Is that it? Yeah, there's no restrictions on this. But we could, I mean, that's not going to be a very wide, that's just going to look like this, right? What if we went 1/2 to make this thing look a little bit fatter? Now we're going to be, here's my vertex, but now I'm going to be out here. A little better? Okay. So here's my parabola now. Now I need another parabola that makes a smile. That's open. Where's my vertex need to be? Okay. So y equals, let's get the vertex in the right spot first. What are we going to say? X minus 4 again, squared. But now plus 1 to move that vertex up here. If we use 1/2 again, we're going to see exactly the same parabola up here. It's not going to be closed like this. So does this parabola that we're making now need to be fatter or skinnier than the one we're dealing with? 1/4? It needs to be fatter so that this thing spreads out more so that it crosses and makes an intersection here so that I have that closed mouth. So 1/4 maybe? Okay? If I plug in 0, let's say, to this equation, then I get negative 4 squared, which is 16. 1/4 of 16 is 4, and then 4 plus 1 is 5. Right. They will cross. Maybe something even bigger than that? 1/8. Okay. Let's try 0 again here. We got 16 here now. 1/8 of 16 is 2. 2 plus 1 is 3. So now we're sitting here. Does that close that smile? Yeah. And then if I reflect that over my axis of symmetry, 1, 2, 3, 4. Now I can draw in that parabola. And I have a closed smile. It's probably a little bit broader than we thought it should be. Maybe if we made this parabola right here a little bit more skinny, then it would look good. But that's the idea. You just made that closed parabola. Perfect. Good. Now what we're going to do in this section is basically exactly what we just did. But now that we've done that, we can find these two intersection points here by using substitution. Once we've done that, at the end of the section, we're going to actually shade in this smile. So let me ask you this. If I'm shading, how does my equations here have to change? I need to use inequalities. That's right. So for the blue inequality, if I want this region right here to be shaded, what would I have to turn this into? Less than or equal to, that's right. So that I'm winding up shading below. And then for my red equation, If I'm trying to shade this region right here, what would this have to turn into? Greater than or equal to. Okay? Once I've done that, then I've now shaded in this region right here. That's the whole idea behind this section. And you already kind of get it, so that's good. So, when you have a system of equations and one is linear while the other is quadratic, there are only three possibilities for solutions. If one is linear and the other is quadratic, which means I'm looking at what's one graph going to look like? A line, and the other one will look like a parabola. So if I have a line and a parabola that I'm graphing, there's only three ways that the graph can look. First, it can look like this, where you have an intersection here and an intersection here. The line is cutting through the parabola. Or it can look like this, where the line is just touching the parabola at one point. And it doesn't necessarily have to be at the vertex. It could be over here, or it could be over here. In geometry, if you had a circle with a line that was just touching the circle, that would be called a what? In geometry. A circle. You got a line that's just touching the circle. What's that called? It's a tangent, that's right. So in this case, the line would be tangent to the parabola. Same idea. And finally here, the line does not cross the parabola in any way. They don't touch at all, which is possible in this situation. So in that case, then there'd be no solution. Here you have a line that's cutting through. In geometry, that's called a secant. Two solutions. Here you have a tangent line to the parabola, one solution. Here you have a line that is not touching the other parabola in any way, no solution. You have two options for graphing a system of equations that involves a line and a parabola, a linear function and a quadratic function. You can either graph or you can solve it algebraically. Typically, algebraically is going to be more accurate than graphing. If you're going to solve graphically, then you need to carefully graph each equation, very carefully. Just like we did when we were graphing systems of equations that were linear. Then determine where the intersection or the intersections are and write the answers as ordered pairs. You have to give me the answer as an ordered pair or it's wrong, just like in systems of equations that were linear. If you're going to solve algebraically, then you want to put both equations in y equals form. We can't call it slope-intercept form because both equations aren't necessarily going to be linear. You won't see y equals mx plus b. Just solve for y. Then set the two equations equal to each other, which is what I mean by substitute for y. Basically what you'll see is the two equations become equal to each other. Then solve for x using any method we've been doing, especially if you have a quadratic situation going on. You're probably going to have to use the quadratic formula or maybe complete the square. Factoring is fair game. Once you've done that, you'll have one or two answers for x. Plug those one or two answers for x into either original equation and solve for y, and you'll have answers. Not just one answer, but maybe two answers. And those answers will need to be written as ordered pairs. So, the directions say to solve each system graphically and algebraically. Because we're solving the same system two different ways, should we wind up with different answers? No, we should come up with the same exact answers in both cases, okay? So which one do you want to do first, graphically or algebraically? Graphically, that's fine. My advice to you is, you see this equation sitting right here? Don't try to graph that like that. Put it in vertex form if you can. Usually vertex form happens very quickly with equations like this. You just have to remember the process. So if you remember the process, it's also like reviewing for the test which is coming up. All right? So let's put that equation in vertex form before we try to graph it. If I do that, then I need to boot the 9 over a little bit and make a perfect square trinomial. Or maybe this is already a perfect square trinomial, and then I won't have to complete the square. Is it a perfect square trinomial? To check to see if it is, take the square root of that, which is 3, the square root of that, which is x, multiply them together and you get 3x. Then double it. Do I get the middle term? Yes. Is this a perfect square trinomial? Yes, it is. So I can write it like one already. I don't have to complete the square. It's already a perfect square. X plus 3 squared. Now that it's in vertex form, I know exactly where the vertex is already. I don't have to go searching for it. I don't have to do x equals negative b over 2a for the axis of symmetry. Most of the math is already done. So, where's the vertex? No. 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 Negative 3, 0. It's here. So I put a dot there. And then what do I do? How about I draw a vertical dotted line for my axis of symmetry? Do I know any other points right now without drawing anything else on here? Yes. I know the y-intercept. What's the y-intercept? It's 9. 9 isn't really on my graph, but I can put it on there and reflect it across to give me a good target to shoot at when I draw in that parabola. So now I can reflect it across, 1, 2, 3, 1, 2, 3. How do I draw in the rest of the parabola? I need some easy points. You got to make a table on this one. X and Y. Choose numbers to one side or the other of the axis of symmetry. I'm always going to go to the easier looking numbers. I think negative 2 and negative 1 looks a little bit easier than negative 4 and negative 5. So I'm going negative 2, negative 1. I already have 0, so I don't need it. Take negative 2 and plug it in. Negative 2 plus 3 is 1. 1 squared is 1. Take negative 1 and plug it in. Negative 1 plus 3 is 2. 2 squared is 4. So I have negative 2, 1, and I have negative 1, 4. Reflect those across, and I can see my parabola now. You need to remember how to graph. Draw on a smooth curve, but remember where those dots are. Those dots are going to become handy for us when we graph the line that we're about to draw. So that's the top equation. The bottom equation is just a line, y equals x plus 3. If you don't know how to draw a line, then we have some problems. Come in and talk to me. We go to the y-intercept, which is 3. And then we graph our slope, which is 1. So up 1, right 1, over and over. Reverse it. Down 1, left 1. And look what happens. I land exactly on that dot. Down 1, over 1. I land exactly on that dot, and then I continue. So I already know what my intersection points are just from drawing those dots on there. This is a line, so I draw in a straight line, not a wiggly line, using something straight. And even though I can't really see it very well, this line does cross through that parabola and then come back out on the other side. It goes through the parabola twice, which means I have two solutions. My first solution is going to be the ordered pair, negative 2, comma 1, and my second solution will be the ordered pair, negative 3, 0. That has to be there. That's the answer. That's how you solve these graphically. To graph to solve algebraically, look back at the steps that I gave you for solving algebraically, and it says, put the two equations in y equals form. Well, both equations are already in y equals form. Now we're just going to use substitution. Because when these two things cross, this y is exactly equal to that y, and this x is exactly equal to these x's, I can use substitution. So basically what happens here, if you want to think of it this way, is you can just take this and plug it right there. Or you can take this and plug it right there. Either way, you're basically setting the two equations equal to each other. So I'm just going to write x squared plus 6x plus 9 equals x plus 3. This will allow me to solve for x. I might get two solutions. I might get one solution. I might not get any solutions. I can use any method that I know of, except for graphing. I can get everything on one side equal to 0. I can factor. I can use the quadratic formula. I can complete the square and use the square root property if I want to. Whatever method you choose will get you to the same answer in the end. So I first have to get everything onto this side, which means I'm going to subtract x and subtract 3 from both sides, which gives me x squared plus 5x plus 6 equals 0. And now from here you can use whatever method you want. Is there one method that maybe makes more sense than another right now? I've heard completing the square and quadratic formula. But actually, if you look at it, factoring is super easy. To factor this one, all I need is two numbers that multiply to give me 6 and add to give me 5. Can you think of two numbers that do that? 2 and 3. So this factors into x plus 2 and x plus 3 equals 0. So to solve that from here, what do? Yeah, use the zero product property. So x plus 2 equals 0, x plus 3 equals 0, which means x equals negative 2, x equals negative 3. Those are the x coordinates for my solutions. Now I got to find the y coordinates. So I take each one of these answers and I'm going to substitute them into whichever equation looks easier to substitute into. Which equation looks easiest? The bottom one, for sure. So for x equals negative 2, I take that and I plug it into the bottom equation. Y equals negative 2 plus 3, which is 1. I take negative 3 and I plug it in, and I get y equals negative 3 plus 3, which is 0. So now I have two ordered pairs. I have the negative 2 for x and the 1 for y. And I have the negative 3 for x and the 0 for y. There's my two solutions. Did I get exactly the same answer? Yes. All right, do you want to solve this one graphically or algebraically first? It does work both ways, but we got to do both. So which one do you want to see first? Graph? Okay. So I will use blue for the quadratic and red for the linear function. The linear one we can graph easily. I'm going to leave that for a second. If you don't want to put this in vertex form, you don't have to, but I really recommend doing that. It just makes life easier. Which way is this parabola opening? Down. I know it's down because of this right here, which means we're going to have a maximum value. That's right. To put this one in vertex form, I need to draw my grouping symbols like that. And then I need to make that A inside 1. Not negative 1, 1. So that means I need to factor out a negative sign. So I have y equals negative, parentheses, x squared plus x, leave a gap, plus 6. Completing the square inside, I divide b by 2 and I get 1/2. 1/2 squared is 1/4. So plus 1/4. Which means I need to, normally we'd subtract 1/4 outside, yeah. But because of this negative sign here, that's actually a negative 1/4 here, which means I need to add 1/4 outside. So now we have a perfect square trinomial. We can write it like a perfect square. Y equals negative, parentheses, x plus 1/2 squared plus 6 1/4. Yeah, I liked the improper fractions better, but in this case, since we're just graphing 6 1/4, it's perfectly fine. Now what? The vertex is where? Negative 1/2. So here, and then up 6 1/4. 1, 2, 3, 4, 5, 6. And then 1/4 is probably right there. And now I can draw in my axis of symmetry like that. The negative sign outside just tells me it's been reflected. It's moving left. Now what? Y-intercept is 6. That's a free point. So you might as well take the advantage of that and put that y-intercept on there and reflect it across. Now I know that I need to set up my table, and I'm not going to choose 0 or -1 as one of my numbers. So give me another couple numbers to pick. 1 and 2. If I take 1 and I plug it in, am I going to like using vertex form here? No. I don't have to use vertex form. I can take that 1 and plug it back in over here. 1 squared is 1, but make it negative for -1. -1, so -1 minus 1 is -2. -2 plus 6 is 4. I avoid the fractions in vertex form doing it that way. Both equations work, so I might as well use both if I can. Take the 2 and plug it in over here. 2 squared is 4, but make it negative, so -4. Minus 2 is -6, plus 6 is 0. All right, let's put those on there. We have 1, 4, and 2, 0. Reflect them. There and there. Should I maybe get a third point? Yes. I don't want to guess down at the bottom because remember, I'm looking for intersection points, and when I draw that line in there, I might not have the correct intersection point. So take the 3, plug it in. We have 9 here, but make it negative, so -9. Minus 3 would be -12. -12 plus 6 would be -6. So I can get that one on my graph. 3, -6 is right here, reflected across. 1, 2, 3 and a half, 1/2, 1, 2, 3. There's my parabola. Draw that thing in there. But pay attention to the dots that you put down, because more than likely, if that line that you're about to draw in goes through any of those dots, it will go through the dots. Draw in your line, y equals x plus 3. It's actually the exact same line as what we had above. So I go up to 3, 1, 2, 3 on my y-axis. That's my y-intercept. And then I have a slope of 1 over 1. So I go up 1, right 1, and look, there's a dot right on top of that dot. Put more dots in there because I got to make a good graph. Reverse it, go the other way. And what do you know? We landed on another dot from my other parabola. Continue making dots. Draw in the line with something straight. And I already know what my intersection points are. What are they? One, 4, and -3, 0. Okay, now we got to solve this one algebraically. I'm not going to use vertex form for algebraically. I'm going to use my standard form. So what do I do? Set them equal to each other. X plus 3 equals -x squared minus x plus 6. Now what? So get everything on one side or the other, right? For sure. And I have a -x squared sitting here, so I'm going to add x squared to both sides. And that means I have to add x to both sides and subtract 6 from both sides. So I'm going to have x squared plus x minus 6. I get equals 0 on the right. I get x squared plus 2x minus 3 on the left. Now what? You can use the quadratic formula. You can complete the square. You can factor. Personally, for me, I'm looking for factoring first because it's way easier than the other two methods, I think. So if it factors, I need two numbers that multiply to give me negative 3, and at the same time add to give me positive 2 are the two numbers that do that. Negative 1 and positive 3. So this thing does factor. X plus 3, x minus 1 equals 0. Then zero product property. X plus 3 equals 0, x minus 1 equals 0. So x equals negative 3, x equals positive 1. And what do you know? We got the same x coordinates we got over here for our ordered pairs. So we're probably on the right track. So take your x equals negative 3 and do what with it? Plug it into the bottom equation, the easier looking equation, and I get y equals what? 0. Negative 3 plus 3 is 0. I take 1 and plug it into the same equation, and I get 4, which means I have two ordered pairs for my solutions, negative 3 comma 0 and 1 comma 4. Same answers we got from graphing. Before we start this next one, take a look at it. What are we dealing with here? Two what? Two parabolas. What do we know about these parabolas already? One is up, one is down. Do we know anything else about these parabolas? They have the same y-intercept. Yeah, look at this. We have a plus 12 here and a plus 12 here. If they have the same y-intercept, then does that mean we already know one of the solutions? Yes. 0 comma 12. Yep. So we already know one of the answers, which is really nice. It doesn't do us any good for finding the other one, but we already know one of them, just by looking at it. All right? So for this one, what should we do? How about we solve this one algebraically first? We did graphing first on the other two. Let's do algebra first on this one. So, what do I do if I'm doing algebra first? Set them equal to each other. I have x squared plus 7x plus 12 equals negative x squared minus x plus 12. Okay, now what? All on one side, so that means I gotta add x squared, add x, and subtract 12. Add x squared, add x, subtract 12. That gives me equals 0 on the right, and 2x squared plus 8x, and then the 12 minus 12 is gone, and I have equals 0. Now what? So you want to complete the square here? How about you divide everything by 2 because you have a GCF of 2? So now I have x squared plus 4x equals 0. Now what? I've divided out the GCF completely. I divided everything by 2. What should I do now? I'm trying to solve for x. You want to complete the square? How about I just solve for x? I don't want to complete the square. I don't want to use the quadratic formula. I want to factor. Can this be factored? We pulled out a 2, but actually that wasn't the GCF. What was the GCF? 2x. So if I'm looking at this now, this equation right here, I don't need to erase it. I can factor out something here, can't I? X. If I factor out x, I'm left with x plus 4 equals 0. Now what? So what do I do next? Yeah, but how? I can't divide by a variable ever. I can't subtract 4. It's inside parentheses. That violates the order of operations. I don't want to distribute because I just factored it out. That would just undo what I just did. I can't. That's not being added to x. It's being subtracted. It's being multiplied. What do I do? Huh? Can't divide by a variable. It's a three-word phrase that starts with Z. Are we not multiplying two things together here? Yes, we are. Something times something equals 0. So therefore, x equals 0, or x plus 4 equals 0, which means x equals negative 4. Now what? Take your 0, plug it in, what do I get? 12. We already knew that one. Take my negative 4, plug it in. Have to do a little bit of thought here. Negative 4 squared would be 16. Negative 4 times 7 would be negative 28. So we have 16 minus 28. Negative 12 plus 12 is, so I get y equals 0 here. Which means I have two ordered pairs for my solution, 0, comma 12, and negative 4, comma 0. This is a really good problem because it reminds everybody that you're using zero product property when you are solving equations. If you factor it, you need to use zero product property. We factored it. It didn't look like the usual FOIL problem, but that doesn't matter. It's still something times something equals 0. Don't jump to the quadratic formula immediately. Don't jump to completing the square immediately. Try to factor it first. A lot of times these things will factor, and your life will be much easier. Plus, it's a good review for the test. So the next thing we need to do is graph this guy. Do you want to put these in vertex form, or do you want to graph them in standard form? Look at the problems. I have y equals negative x squared minus x. If I'm putting that in vertex form, not only am I going to have to factor the negative out, I'm going to have to divide by 2 to that b and get 1/2 and deal with 1/4, and then I'm going to wind up with some sort of fraction outside. I'm not going to like that very much. Look at the next one. If I divide by 2 on b, then I have 7/2. When I square it, I'll have 49/4. Does that sound like a lot of fun? Not really. We're going to have to deal with fractions anyways when we try to graph both of these. But there's no sense in making vertex form out of it when we just go back to this form when we try to plug in points. Because we're going to pick easy numbers. And those easy numbers aren't going to be easy when we're dealing with fractions. Okay? So in this case, I'm not going to go to vertex form. So take a look at what it is that you're doing before you try to decide if you're going vertex or not. These numbers right here, that negative 1, that negative out front, that positive 7, that's going to be ugly going to vertex form. So I'm leaving it alone. I'm going to graph it as is, which means in order to do that, I'll need to start with the axis of symmetry. AOS is x equals negative b over 2a. So negative 1, which is just 1 over 2 times negative 1, which is negative 2. So the axis of symmetry is x equals negative 1/2. Put it in there. Then I just got to take negative 1/2 and plug it into my equation here to get my vertex. So negative 1/2 squared is positive 1/4, but make it negative. So we have negative 1/4 sitting there. Then we have negative 1/2, which makes positive 1/2. So we have negative 1/4 plus 1/2. Positive 1/4 plus 12. 12 1/4. So I'm going to make my table here, x and y. I just plugged in negative 1/2, and I have positive 12 1/4. Which way does this parabola open? Down. So I'm going to have to get all the way to 12 1/4 on my grid here, which means my y-axis needs to go by 2's. Now from there, I need to just pick easy numbers. on one side or the other of the axis of symmetry. I already know that I have a y-intercept of 12, so I can put that on there. 2, 4, 6, 8, 10, 12, and then 12 1/4 right there, reflected across. So I already have 3 points drawn for my parabola, and I haven't done anything extra yet. I need to pick some smart numbers here. I'm going to go with 1 and 2. And now I'm not dealing with fractions anymore. So I take 1, plug it in. 1 squared is 1, but make it negative. So that's negative 1 minus 1 is negative 2. Negative 2 plus 12 is 10. Take 2, plug it in. Squared is 4, but make it negative. So negative 4 minus 2 is negative 6. Negative 6 plus 12 is 6. Probably going to need to pick some more points here, but we'll see. So I take 1, and then 2, 4, 6, 8, 10, 2, and then 2, 4, 6. Reflect them across. Maybe I pick another ordered pair here. Try 3. 3 squared is 9, but make it negative, so negative 9. Negative 9 minus 3 is negative 12. Negative 12 plus 12 is 0. So I get 3, 0. Dot there. Reflected across. There we go. Maybe that's enough. Drawing my parabola. Actually, I already know that it is, because I have negative 4, 0 on my graph and 0, 12 on my graph. So my line is going to go, or my other parabola is going to go through like this. We'll finish that up next time.